All right. Hi. Um, so we have looked at some of the stencil computations. Then we started looking at some of the non-stencil or more like direct solver methods. And we looked at uh, the try solver method in the last class. Today we are going to look at LU as well as LU decomposition, that is without pivoting and with the pivot given. So let's look at LU first. So LU decomposition without pivoting means that we are given just a matrix A and N and there is no other vector given to us. And we want to transform this matrix into L and U form. Right? So essentially we have a lower triangular matrix L and we want to produce another upper triangular matrix U such that A equal to LU. So it can be, I mean, as we have discussed earlier in earlier classes during OpenMP and MPI, this method can be very useful in many applications. And we could also transform it as part of equations, rather recursive equations, I would say. So to at a higher level, these look like recursive equations. For example, if you look at Uij, that is dependent on Ukj, right? So it might look like these are recursively dependent on each other, right? So L depends upon itself as well as U. However, when you look at the indices, you realize that that is not really the case. For example, U of ij is dependent on U of kj, where k is going from 0 to I minus 1, right? And therefore, it never happens that U of I is dependent on U of I. So this is a nicely sequential code, right? So you are using everything from before to compute the current value. That is from 0 to I minus 1, you are using to compute U of I. Right? So does there still exist enough parallelism in this? And similar thing happens for L. Well, it turns out that yes, there exists enough parallelism, just that we have to exploit it at appropriate levels. And that's what we are going to see in this particular lecture. All right, so let's look at lu.c. So this is our lu.c. The main turns out to be simple. It just has a type which is currently has defined to float, but you can change it, which is defines an array. Then we are going to initialize the matrix using some initial values, similar to what we have done earlier. And then I just call LU, and then finally I print the matrix just to see if I get the L and U properly. Well, I mean, whether I keep L and U as separate matrices or whether I store it inside A, that is also one decision which we have to take. One thing is, of course, if you have very large arrays, and LU decomposition might not be happening on one matrix. You might have a range of matrices on which you want to run LU decomposition in parallel. In such cases, the memory requirement might go on increasing, and if you are not requiring A as such after this LU decomposition, you might as well want to make use of it further. If you are actually interested in retaining the value of A, that retaining the original matrix A, then it makes sense to copy L and U separately into different matrices. Alternatively, if you are going to use L and U at different places, you can as well make use of another matrix B, which is actually a combination of L and U. Right? So there all these mechanisms exist, and you will have to decide based on your situation which one is going to be useful from the perspective of well, memory in one sense, but in the second sense also performance. When you are copying it to a different matrix, you don't have this self-dependence computation happening. For example, as we will discuss, there will be this A of ij is dependent on A of ik as well as A of kj. So there is a reading as well as writing happening. And in such cases, if as long as you are reading and writing to two different memory locations, it's all right. But in parallel, you can get into issues. And therefore, if you want to create a separate copy, even if it is increasing the memory requirement, it might actually end up giving you better performance. So you have to look for both the space as well as time constraints in your application. Um, yeah, so initialization of the matrix is, I'm not going to go into that. That is going to be as before. But as far as the LU decomposition is concerned, it just follows the equations where we have a nested for loop for I as well as j, and then there are two such steps happening, one for the L part, another for the U part. So in this case, for one particular, for example, if you notice this, there is going to be yeah, so there is going to be a k loop which is going to be within that I and j loop, and that is required for both of them, both L as well as U computation. So that is going to be another loop inside j, and that is going to make it a triply nested loop essentially. But this is not in a standard form. That is, it's not that for I, j, k is continuously occurring, although it seems to be occurring here. But that j loop is not one loop inside the I loop. There are two j loops which are concatenated, appearing sequentially in this loop. So collapse 3 might not be the right thing to do in such cases. In fact, it will not compile also. Okay, so but let's stick to this as our basic implementation. So again, I would reiterate that once you have thought about, I mean, your problem statement will give you certain aspects of domain specific knowledge to be encoded as part of engineering equations. And once you have converted those into equations, then mapping those to your program turns out to be relatively easy. So that's what I have been doing, where we have those equations available for a particular numerical method, and those I am trying to map to the program, sequential program, and then we try to parallelize it. And the mapping from your domain knowledge to equations, I mean, depending upon your domain knowledge, it can differ. It will require, depending upon what branch you are in or what kind of problems you are looking at, these will differ. Similar to earlier programs, to avoid any end conditions like overflows, underflows, etc. Whenever there is a division, we are trying to avoid division by 0 or division by very small quantity by making sure that A of jj, if it is greater than epsilon, then you divide it by A of jj. Otherwise, you just leave it as it is. So that is what we are doing here as a small change with respect to what this does. Right? So this U of jj is this division. It should not underflow or overflow. That is the caution which we are taking in this code. This one might differ depending upon what your application is. So it should make sense in the semantics of your application. All right. So this part is fine, and when we try to, let's say, compile it and run it, let's say that I specify n equal to 10. That is okay for now. So lu.c, let's try to do that. (078). Okay, so I get some values of this matrix, which are the which is the modified A matrix. So we can assume that there is L and then U both encoded in this matrix. So okay, so now let's try to parallelize this, right? So assuming that you have made sure that the sequential code is working correctly, etc., and it is giving the correct answer. Let's say that now you want to parallelize. Obviously, we want to first take care of these data types, right? So let me just go to u1.c. Where we don't want A, since this is happening in different functions, the first thing that we do is hash pragma SCC data. We create the matrix A, as well as copy out the matrix A so that I can print it on the host, right? So that is one way in which we have used the data clause, and this seems to be now standard with respect to all our algorithms that we have been doing, where we create the input matrices, then initialize those inside, and then copy out the resultant matrix or a vector. And as we also know that if this would have been read directly from a file, which means that this initialization would have happened on CPU. In such cases, we could have done copy in of A, right? And then if it's the same matrix for which we are doing copy in and copy out, we can as well convert it into copy A. Okay, so this is the basic aspect of the data communication between CPU and GPU that is taken care of. As far as initialization is concerned, that is similar to the discussion is very similar to what it was for triangular matrix solver. So that I'll skip here. Let's directly go to LU part. In this LU, now I have, let's say, for I, for j, for k. And as we discussed, we don't have the flexibility of using the nested parallelism. And therefore, I want to decide where to put this ACC parallel loop. So one way to do it is to put ACC parallel loop here only for I. Okay, that is one possibility. So I can put a pragma here. And maybe it works fine. So it will work fine, just that you have to measure whether you are going to get good performance out of this or not. So I loop is going to be in parallel. As far as J loops and K loops are going to be there, those are going to be sequential in nature. Right? So let's actually, I'm just going to comment this out and let's measure how much is the performance that we get when we try to parallelize this only I loop. ACC parallel loop, we say that all of this is present, num workers, etc. Okay, A is present, num workers of n, etc. So all of this is there. I can as well try collapse 2 since it is there. Okay, so now let's try to okay, so what we would do is that, I mean, it doesn't make sense to compare the time for 10. Let's make the matrix a little larger. We'll have 1024 elements, but I don't want to print those 1024 elements, so I'm going to comment out this print mat. Let's see. So lu1.c is the file name, so let me change that here. And we are going to do a submit. Coming out of VI. Okay. So Q sub 209080. Okay, loops associated with collapse clause are not perfectly nested, right? So this is one issue with respect to our lu.c and their lu1.c, and therefore whatever we have tried, that doesn't seem to be working as far as that collapse clause is concerned. So what is the issue here is that this collapse clause, it says that the loops are not perfectly nested. What does it mean? Well, it just means that within I loop, it's not that only J loop is present. Actually, there are two steps which are present inside the I loop, which is going to be for J and another. Such two statements are present. It is not called as a perfectly nested loop. A perfectly nested loop will have for I, for J, and then some processing inside for J. There is no other processing inside for I. Right? So therefore, collapse clause doesn't allow us to to be used at that location. Okay, so no, not a problem. We are going to remove that and let's see if that works out. Still running, looks like. Okay, so it's done. Let's see if it did what the compiler said. The compiler, as far as initialization is concerned, it collapsed the clauses, etc., that we have discussed. But inside the code, it tried to do some parallelization, but there is lot of sequentiality. Where is the sequentiality coming from, and where is this parallelism? Well, this parallelism is what the I loop is, which is line number 38. On line number 41, we have J loop and K loop, the first J loop and K loop, and then line 46 and 47, we have another J loop and K loop, right? So that is what is the information with respect to those that gets printed here. So that is okay, that we have not parallelized anyway, so that part is all right. Let's look at the results in terms of the time. And as you noticed, I had to do of the output multiple number of times, and it took really some time. So as far as init mat is concerned, total time is, let's say, 52, I think this is microseconds. Okay, that is anyway going to be very small, so we can ignore that. There is some time shown for main, which is around 348 microseconds. That is also something very small, which we can ignore. But as far as LU method is concerned, which is going to be our important method, that seems to take a very large amount of time. It actually took 1.46 seconds for the processing, and that turns out to be really, really large. This doesn't seem all right. And if we take this much time for 1024 cross 1024 matrix, we are going to require much larger time for sufficiently larger matrices, or when you have more matrices with you to be processed. So this is not going to work out with us, right? So we have to do something about it, and that is where this moving to J might come into play, right? So what is the advantage of moving to J? Then I can parallelize both the J loop. The I loop is going to be sequential, but the J loops, both of them are going to get parallelized, and let's see if that gives us any benefit. Another aspect which is probably going to help out is this collapse clause. So whether that is, what about this? This does seem to have some statement in it, so it may not allow the collapse clause there. Let's see. We will try to use this nested, parallelization of J loop rather than the I loop. Okay, so there is some problem, as we were anticipating, that the collapse clause is not allowed at that location, line number 42. But remember that we got error only at one place. We didn't get error for the other place because that, oops, because this loop is perfectly nested. The second J loop is perfectly nested, whereas the first J loop is not perfectly nested. There is another statement. So there are essentially two statements. One is for this one statement, and another is this A of ij, right? So there are two statements in the J loop, therefore this is not perfectly nested, so I can't parallelize this. But let's see if we can now get rid of that and see if this works out. And remember that we required 1.46 seconds in the earlier case, right? So let's see what happens now. Well, the total time has actually come down considerably, right? The other times have remained the same, 50 and 348. Anyway, there won't be any difference that those other times might be making. But then there are other times, right, which are shown here. The first, so there was only one parallel, let's say, scope or parallel loop, which was for I in the earlier case. So we got only one time, which was, let me just show that. Yeah, so this was printed exactly once. The kernel launched was only once, but now there are two different kernels, two different parallel regions. So one was launched 0.1 number of 0.1 seconds, and another was launched for 0.047 seconds, right? Or 46 milliseconds or 47 milliseconds and 119 milliseconds. So this seems to be an improvement over what we had with respect to the original case, right? So this should be remembered. So parallelizing this turned out to be better, and parallelizing using collapse clause turned out to be considerably better than not having that collapse clause, right? So this was helpful. You can also see where that collapse clause is working out. For example, when there is no collapse, you see that the grid dimension is 1 and the block dimensions are 1 into 1024. Whereas when you have the collapse clause, this ranges from 1 to 1023 and the block remains at 1024. So there is some nice parallelism with the collapse clause. Again, collapse clause is not the holy grail. It will not give you always performance, as we have seen in one of the earlier cases. But at some times, it can actually become very useful. Okay, so that seems to be all right. But is this the end of the world? Well, I have specified this num workers n. Is this something which is always going to be useful? We can check that. For example, if I can just remove this num workers n and allow the compiler itself to figure out, let me remove that from both of them so that we can compare. Um, So allow the compiler to figure out how many threads to use, right? Rather than I specifying. Then let's see what happens. We had 119 here, that became 112. This was some, I think, 46 or so, if I recall correctly. And yeah, so that seems to be 50. So this much difference you should not worry too much about, because this is, I mean, 5 to 10% error here and there can occur because of the way threads get scheduled, etc. So that much difference is probably all right. If you run it again and again, then we have to take the average and then talk about the averages, compare averages rather than a single execution. So there doesn't seem to be too much difference. There is some difference though, and it has affected both the loops in a different way, right? So as you can see here, this is the block size is now 128, which means there are 128 threads within a single thread block, and that has improved performance for the first part of the first J loop. Whereas when you have 128 threads per thread block, then the number of thread blocks increase because of the collapse clause, has resulted into increased execution time a little bit, maybe 4 seconds in this case. So for the second J loop, so this is okay, and it's not really going to hurt you whether you specify it yourself or you leave it to the compiler. Okay, so this part is fine. Now, is there anything better that we can do out of this? So let's see, we have lu2.c, right? Well, lu2.c is the same as we had started with, so that is the worse part. So let's go to lu3. So what I have done here is I have added this hash pragma ACC loop, right, for the J clause. So we are not allowed to do parallel multiple times, but I have tried to do hash pragma ACC loop here as well as here. And what we would like to see is whether this has any benefit in terms of performance. And we would like to see that performance now. So this is LU3. So let's remember these times. One was around 112 milliseconds and 50 milliseconds. So 23. So this was 100 and no, sorry, this was init mat. So this is okay. Now things have changed considerably. Now there is again a single parallel region. So things have been combined, and the amount of time that is taken is now 3 milliseconds or 3373 microseconds, which is considerably lower compared to what we had with respect to this. So 112 milliseconds plus 50 milliseconds, right? These were the two compute regions. And where is this coming into play, right? So this we should analyze a little bit. So let's see. Okay, so one of the things that has been reached is that data region reached 2 times, right? So this is one place. Whereas the data region is reached multiple number of times here, 2048 times and 2048 times. So is it that it is copying those many number of times? Could be. Let's look at that here. No, but A is already present, so I think it will not cause any issue. So this is not related to the data clause, so that is ignore that. So this is definitely happening only because of the way the loops are getting kind of parallelized when we have this hash pragma ACC loop inside, right? So here the block size is still 128 because we have not specified the number of workers, etc. The grid size is 1024, which seems to be reasonable. It's not too large, it's not too small, and that is probably giving us this performance benefit, right? So this is the step-by-step improvement in our code, and there exists some science with respect to, or some fixed way or some fixed optimizations which we have done with respect to, let's say, the data copying, reducing the communication, etc. But there are some which are data dependent or situation dependent. So you need to look at the context, you look at the sizes of the data, and then decide which one is going to help you in general, right? So this was about the LU decomposition. Let's go without pivoting, right? So let's go to when you have a vector given to you as a pivot. So what happens in that case? Let's go back to slides. Okay. Right. So we looked at LU.C. Now let's look at the LU decomposition, so to say, which essentially is solving a system of linear equations. Again, we have seen this solving of linear equations earlier in the context of MPI as well as OpenMP. We are going to use the same method, which is using the forward and backward, which internally uses the forward and backward substitution after LU has been done. That is, after A is converted into L and U. Right? So the problem statement is that you are given a matrix A, and this time you are given another vector B, and we want to produce X and Y. Sorry, we want to produce X such that AX equal to B. Right? So that is what is the computation we want to perform. So this internally is going to use LU, and as we have already discussed in one of the lectures, Ly is same as B and Ux equal to Y, so where this Y is same as this Y. And so it is going to make use of the LU part that we have seen so far, and after that it is going to do the forward and backward substitutions. Right? So if you look at the LU decomposition into the equations form, then it looks something like this, and we are now experts in converting equations into a parallel program, or rather first sequential program and then the parallel program. So that can be nicely done. So this is going to be an I loop, then this is going to be a nested loop, so which is going to involve K, then there is going to be a multiplication of quantities, so Bi is going to minus that summation. So once you have found this out inside a loop, that is going to be subtracted from Bi, and that is how you will get Yi. And similarly for Xi, where there is going to be instead of L of I am going to divide by U of I, and as we have discussed, there is going to be some small epsilon check which we have to make just to ensure that we don't get into underflows and overflows. So LU decompose.c is what we are going to look at now. Okay. The main part remains the same, except that now we have a few more vectors. So it's not an in situ update on A, but I'm going to fill up X and Y. As far as B is concerned, that is going to initialize B, which might be coming from somewhere. I'm initializing those with some values. Then I perform LU, which is exactly the same as before. In addition, I need to do a decomposition. So let's look at decompose for the sake of our understanding. So we want to have bi minus summation, right? So that summation is going to get captured inside, let's say, some variable w. You could have as well used yi directly here. So this could have been yi minus equal to something. In this case, I have just started with a local variable w. Right? So either way, it should be okay. Sometimes there might be a small performance difference because of using a local variable versus writing to yi, because there will be some caching effects which will come into play, because the other threads are also writing to, when you parallelize this I loop, the other threads are writing to y0, y1, y2, y3, right? So all of these are writing in parallel, and that can get into some performance issues, something called as false sharing, where when one thread is writing to y of I, another, I mean, since that cache is going to get invalidated, and the cache is going to contain all of these words together, the other thread will feel that, oh, this is now written by the other thread, so let me push back this. The cache is going to push back the data to the global memory, and then the another thread which is running on a different core will read that data again to make sure that y of 1 is now read and written to. And as soon as y of 1 is read, then the 2th thread is going to again fetch the data directly from global memory, because 1 has already invalidated the cache line. So it so happens that the cache uh, line is going to store all these words, but the cache line is going to get invalidated, but it is going to get invalidated for a different data item than the one that the other thread is interested in. So this kind of sharing at the cache line, which is essentially false because they are writing to independent memory locations, this is called as false sharing, and this can degrade performance on CPUs. Um, so okay, so that an aside, but if you have a variable like a local variable or a private variable, then that is going to be easy, because you are not going to write to yi until inside this loop, right? So you are going to write it only later. At that time also false sharing can happen. For example, if y equal to w happens uh, uh, for all the threads in parallel on CPU, but then that is going to happen only once. If you would have had y of ii here, then the cache invalidations would have recurred many number of times. All right, so this is computation of y, and this is going to be the computation of x, where again we are going to make use of this div. Did we miss out on some part? There was there should have been a division by L of ii. Did I miss that? I equal to my bi minus summation. All of this should be divided by L. Yeah, it probably would have, this should have been probably divided by the same. Similar to here, where we have the division happening with respect to a of, in this case, n minus I, that we are, so this is probably implemented in a slightly different way. But anyway, this should have there, that division should have been there, is what I feel at this stage. Okay, so let's see how, from the parallelization perspective, if we'll be able to parallelize this, and whether there are more complications that occur compared to the LU part. The LU part remains the same, right? So LU is a separate function which remains the same. Right? You could combine the two, that is not a problem, because parallelization is anyway going to be separate for the two. All right, so let's try to parallelize this, and obviously the first thing that we will do is to do a data clause for this part, and that we will have in decompose 2. So we are going to have init matrix of A and B, and therefore I'm going to, so note that in this equation, although this L and U are appearing in the equations, since our LU was in situ update, we have it available directly as part of A, right? So therefore we are just passing A as a parameter. All right, so A and B get initialized, and therefore I just have creation of A and B. But along with that, I have X and Y as the output variables. So I need to also create X and Y, and then copy out them at the end of this data block. So that part is okay. And then decompose A, B, X, Y. Let's look at the decompose part first. The rest of the code remains, LU part remains the same. Initialization also remains the same. So let's look at the decompose part. Now, let's see. So we have this hash pragma ACC loop at the outer I level, and then I can as well, similar to what we had done for LU, I can have for the inner loop for hash pragma ACC loop, and there is a W minus happening. So therefore, I might want to do a reduction onto this W using the minus operator. Okay, and a similar thing is happening for the J loop here, right? So the parallelization of these two uh, uh, loop nests is going to be almost the same, right? So let's see if this works out. So we again, let's increase this to 1024. That part is okay. I'm going to, okay. I need to change the LU decompose 2.c, right? LU decompose 2.c. Okay, so if you look at the compiler output first, right? So there are a lot of different functions init vector, because there is initialization of vector also. So that is fine. Initialization of the matrix, that is also parallel, and I'm also using collapse. As far as LU is concerned, the outer loop was parallel. There was one inner sequential loop for K, so that part is as before. As far as main is concerned, we have created, copied out, etc. Created A and B and copied out X and Y, so that also seems optimal. As far as decompose is concerned, it's generating a parallel loop for 55, line number 53, which is the I loop. Then line number 55 is going to be the J loop, the first J. Here also there is going to be 63 is going to be another J loop. And then there is also generation of the reduction, etc. And it says that loop is parallelizable. It seems to be doing fine. So as far as the code is concerned, it seems to be giving good parallelism out of this. So, yeah, so that is the compiler output. Now let's look at the output of the profiler. So as the code ran, init vector primitive, it took some 17 or so microseconds, which is okay. Init mat internally used init vec, so that took 59, which is similar to what we had earlier. LU part took 3000, 3.3 milliseconds. That was similar to what we had from the last LU, because it is as optimized. Main took 43, and decompose had two parallel regions, and one of them took 20 microsecond, another took 19 microseconds, right? So this turned out to be much better compared to the LU part. So the LU part is the one that is really causing the that is really consuming time, but otherwise this is not the decompose part is not really taking much time, right? So this part is okay. Is there any other thing that we can do? There isn't anything else. But one thing which I wanted to highlight is that, again, if we try to do this removal of this loop, right? So if you just parallelize this, because we are not allowed to use the collapse clause again, then we are going to again see a large performance difference with respect to the optimized one, right? So 123. Remember that these are in 2 digits, 20 and 19, right? So 20 is what we will remember. Well, this seems to be okay. 21 and 20. This also seems to be all right, right? So what is happening? So if I don't do a reduction but run it sequentially, right? So that is what is happening. Is LU decompose 2, that is correct. And I have commented this out. So as long as you are, oh, so only this one is the dominating part, which is anyway taking a very small amount of time. And even if you don't have the inner loop added to Pragma, it is still performing reasonably well. That is a little strange to me actually, but anyway, if it's performing well, that's usually a positive sign. Okay, seems to be all right. Even if you add, okay, one thing which I would like to do is to remove this reduction. Let's see what happens when you try to remove reduction. Okay, let's see. Come on. And 27. That also does not create any issue. We'll have to check. Okay, so okay, in all these three different situations, we got almost the same amount of time with respect to the decompose. Anyway, the time is really small for making any difference. But as far as this LU time is concerned, that is the one that essentially dominated the overall execution time, which essentially also means, and this is what we do when we try to optimize our codes, is that if you want to put in your efforts, don't put in your efforts in the decompose, because the execution time is anyway small. So what uh, we studied as far as Amdahl's law is concerned is that the sequential part becomes the bottleneck, right? So this is the one which is essentially taking the largest amount of time currently, and even if you remove this 20 I mean with as much effort as possible, this 3404 is still going to be there, right? And therefore you are not going to see much benefit even if you reduce this 20 to 0 for that matter. So our efforts should get focused on this part. In case there are other methods, for example, sometimes you won't be able to go beyond a certain limit by applying different optimizations at the code level. In such cases, I mean GPU specific optimization or OpenACC specific optimizations. In such cases, if you still are not getting as much performance as you need, most probably you need to change your algorithm, right? So for example, you have to see that you are currently using LU, but is that the best algorithm that you should be using? Maybe you should switch to some other algorithm, and then it might perform better. So algorithmic choice is definitely an important criteria to figure out to optimize your overall performance. Within that, then there are multiple implementations of the same algorithm. All right, so we'll stop here, and that kind of completes our discussion on most of the numerical methods that I wanted to talk about. We'll do something interesting in our last lecture. All right.